Okay, today we are going to keep talking about and hopefully finish up this time our lectures on parts of the observable systems, I guess on differential, dynamical systems in general, but we're going to quickly talk about parts of the observable systems. We're going to talk some about differential algebraic equations, which are how we they're kind of a little bit more specialized, but they are important for power flow analysis because this is how we represent the dynamics of generators all operating under power flow constraints. And then finally, we'll talk about stochastic systems. The majority of what we talk about here has focused on the deterministic case of systems, right, where we have systems that we know how they're going to evolve. But when we start talking about either systems with just some randomness in them, maybe there's just, I guess you could argue about what level there's really randomness in the true world, but at least in our representation of systems, there may be some randomness due to things like just unmodeled effects of the system and things that we can't predict. So in this case, we want to model these systems as not deterministic anymore. We want to actually account for the fact that we don't know how they're going to evolve for sure. We want to address that. Now, let's talk about a few formulations of stochastic systems. In general, these are very hard problems, but we can solve some special cases. I'll talk about a few of those, including linear Gaussian systems, which are when you have a linear system with particularly multivariate Gaussian noise. And then also I'll talk about MDPs, which in general are capture a very general set of dynamics, but we can typically only solve them when we're talking about discrete states or discrete actions. So I'll cover all these today. Before I get to all that, though, that should be on the next slide. Some people have handed these in already, so the midterm report is due today. You can email it to me tonight if you want. It's fine. I'm, again, mainly looking for these to be handed in. The homeworks, I'll try to stick with the beginning of class, but you can email me if you haven't handed one in. And actually, if you did hand it in, also email me, just because I tend to respond, give comments via email, and that's just an easier way to list them all. So do email me the reports as well, even if you handed it in. But of course, it's fine, whatever timing works for you today. The other thing is that the next homework is due next Tuesday. And so because of this, we're going to have additional office hours on tomorrow. And in fact, I'll send out an email shortly, but yes. The idea being that you want to have more office hours right before an assignment's due. So we'll have them Monday as well. Longer ones on Monday, in fact. But tomorrow we'll have them, so extra office hours. They're in my office, which is GHC 7115, and it's tomorrow 10/9, 3 to 4 p.m. Hopefully I got that in the camera view there. But it's very skinny, right? Very skinny writing there. Sorry, 11. Yeah. It's not in the past. I'm not just letting you know. Tomorrow's the 9th, right? Yeah. So it's tomorrow from 3 to 4. And then we'll have them again. I'll send out an email that has all this information, but then we'll have them again next Monday. Next Monday we'll have longer ones. In fact, we'll have them for 2 hours. Extended office hours next Monday. The final couple more things, then the next homework will be out on Thursday. And then the next week is Thanksgiving. And actually, due to some travel, I probably will not have class the Tuesday before Thanksgiving. So you have that day off. I don't know if this is a common thing, but that seems like a lot of people travel then anyway. So we'll just have it off before that. I mean, I'm traveling for other stuff, but you all get that week off too if you want it. So we're not going to have class the week of Thanksgiving, and then we'll have the class of 2 next weeks, though. And then the problem set is going to be the last problem set is going to be due the last day of class. Now, right now, the final report is due the last day of class, too. And actually, I will probably change that to be due the day of our midterm, I believe. Actually, does anyone know if is that allowed? Universities have strange rules, right, where you can't have something due on the day of a midterm because it's sort of or it's the day of a final, rather, because it's your study days. Sorry, I meant final, not midterm. Is this sort of a common thing to have final projects due during that exam week? Does anyone know? Does anyone have a problem with that, I should say, actually? If you do, it's really okay. I don't actually know yet if this is couth or not, but probably I will push the deadline for the final report back a week or so, just so you actually turn it in during the study weeks there, rather than the last day of class. So you don't have to have a problem set and a final project due on the same day. I'll have this all in an email. Yeah, I'm just letting you know for now that I'll probably change that, because I think right now in the report for final projects it says it's due at the last day of class, and since we have a homework due then also, because I want to give the week, I don't want to count the week of Thanksgiving because we're not going to be having class there. So therefore, I will have the final project, the final assignment due the last day of class, and I'll just also have the final reports due a little bit after that. But yes, I sent this all out in an email today. Don't worry, but I'm just wanted to check here that this works for everyone, this kind of schedule. And if it doesn't, and if you're not in here in class and you're watching this on video, just let me know over email. I think that is it for announcements. But are there any questions kind of about the upcoming schedule?
Yeah, so one more question.
Yeah.
Next Monday also have office hour? Or?
Yeah, next Monday I'll have them. They're normally 2 to 3 on Mondays, but I'll have it next Monday from 2 to 4, just to give even more time before the problem set's due. And again, I'll send that out in the email, just to clarify all this. But yeah, tomorrow it'll be 3 to 4, and then next Monday it'll be 2 to 4, the office hours. Yeah, so we're talking about final projects and everything being due. It's like it's starting to be almost the end of the semester. It's amazing. Okay, so today we're going to try to get through all the rest of our lectures on dynamical systems. And in particular then, so we can start talking next time about control. We might not quite get through all stochastic systems, but hopefully everything else we'll get through. So as I mentioned to you last time, I started talking about last time, a big issue with lots of systems is we don't actually know what the whole state is, right? We only get we only observe some variable yt, which is some function of the state, not the whole state itself. Let me move this cursor over. We only observe yt, which is some function of the state, not the whole state. And typically, we're talking about cases where we observe fewer dimensions than the full state is, because if we observe as many dimensions as the full state, or we could just directly invert this function h, then it wouldn't really be that interesting, right? Because we could just act as if we observe the real state. We're talking here about cases where you can't. So the big question now is, we know that given a single measurement, we cannot uniquely determine what the state is. Right? If you are given only the temperature in 1 or 2 rooms of a building, you cannot determine what the temperature is in all the other rooms. Right? Just with one reading one time. Similarly, if you just get if you are in somewhere in 2-dimensional space and you get a range measurement to some known beacon, you cannot determine where you actually are from that. Right? You could be anywhere on a circle, essentially. So the big question is then, can we figure out what the state is, or what state we're in, not from one measurement, but from a couple measurements? Maybe we can then, right? Because if you get 3 measurements, for example, and you could track your position sort of changes exactly, then you could use triangulation, right? If you get 3 sort of distinct beacons, then you can find out where you are in space. And similarly, like the case of, there actually is this very kind of nice duality here between this and the controllability case, but we won't worry about that quite yet. But similarly, it turns out that if you have thermostats in 2 rooms and you can see multiple time steps, well, then you can maybe imagine that you will observe the change both due to sort of your current temperature, but you'll also observe how the temperature changed depending on what other rooms were what their temperatures were, and you actually can infer what temperature is in all the 4 rooms if you have thermostats in 2 of them. Again, it has to be a certain two because there are these weird cases in that one particular case, but for having the two next to each other, you can actually do it. The question is, when is this actually possible? And how do we go about doing this when it's possible? Right? So the basic idea is that we are starting in some initial state x1, right? And we don't know what x1 is. And we don't observe x1. What we do observe is y1, which equals h of x1. Then we take some control, go through the dynamics of the system, and we end up in some new state x2. But x2 in particular, we're assuming here through all this that we know what these functions are. That's important. I'm not talking about this today, but maybe next time I'll mention briefly. When you don't know what the functions are, then you have more trickier situation here. But you can imagine there might be learning techniques you can also do to sort of figure out from data what your system might be actually doing. But we won't worry about that here. Here we're assuming that we know what the dynamics are and what the observation function is. So we take some control action u1, and we end up in some new state, which is in this case going to be f of x1 and u1, right? That's what x2 is equal to. And so then we observe h of this new state here equals this. And just for the sake of it, it's written on the board here, but I'll do it again. Now we take, this becomes x2, so we take f of x2, x1, u2, u2, take h of all this, and that becomes y3. And I'm writing it this way because it's important to know that the only thing that we don't know in this case here is x1. I don't want to write it as x2 because then it might seem like, oh, well, we have many unknowns. We have x1 and x2 and x3. Those are all unknown. But remember, this is all deterministic. So if we know what x1 is, and we do know our control actions, because those we sort of, this should be u1 here. We know our control actions because those we input ourselves into the system. So if we know what x1 is, we can just plug it into our function and determine what x2 is. And similarly, we can plug it in again and know what x3 is. So really the only task here, the only real unknown, is this initial state x1. Right? Everything else here is known. So in this whole situation, and remember the dimension of y is a p-dimensional variable. So in this case, what we have is we have n unknowns. And that's x1. And if we get k total observations, then we have k times p knowns. And that is going to be y1 through yk. And these are sort of can be kind of nasty nonlinear functions. But we've already know how to do this, right? If we have some set of equations, and actually if there are more than n of these, if this is greater than n, then some of them are going to be redundant, so we don't even need those. So what we can do is we can just pick n of these total knowns, and then use Newton's method to determine what did the x1 have to be that makes these things all equal here. Right, so for example, we can use Newton's method. Does everyone understand the story? How do you use Newton's method there? I mean, remember, I keep saying Newton's method is essentially a way of finding a zero of a function. But here, let's assume that just we sort of have two of these, right? So our function, which would be a function of x, I shouldn't use f here because I've already been using that, but I guess g of x1. We're trying to find some function g x1, or some value of g x1 equals 0. Some value of x1 so that g of x1 equals 0, where here g say that k was half of what n was. So here g of x equals y1 minus h x1, and then y2 minus h f x1 u1. Right, so this is a function that takes as input n variables. I'm assuming here that k is just half of n, just for simplicity. Of course, you can do it in the general case too. So there are n different outputs of this function. And when this function equals 0, this means that our initial state exactly produces those outputs. So when I say we use Newton's method to solve these equations, what I really mean is we set up some system like this, and then we use Newton's method to find a root of this system. And that is a x. The only x, or rather, I guess if it's nonlinear, there can be more of them, more than just one. But if we find some x1 such that this equals 0, we know that that x1 could have been one of the states that generated this set of observations. Now, in general, again, I'm sort of treating Newton's method as kind of this black box, as if it's just able to find these solutions. And in general, this is a hard thing to do. Especially, I mean, Newton's method, remember, it's kind of a local search method. So you pick some initial value, and then you try to search sort of nearby values to find out where it is. And it works really well for power systems, but there's cases where it doesn't work so well. And you could have it be the case that you give it some initial value of x1, and it just blows up. It doesn't ever find a solution. So you have to kind of initialize it with some guess of your state that maybe is kind of close to the real state. And then it'll work. Otherwise, it might not work. So in general, this observability problem, it's called, can we determine what the true state is given observations? That's very hard for nonlinear systems, or it can be very hard for nonlinear systems. Right? You can do it with Newton's method here. But it's still tricky. It's not like if this is an exact science here, because you need to get a good guess of your initial state maybe. You need these functions to be kind of well behaved, for example. If they have really sharp discontinuities, this could just not work at all. So all these things come into play here. And so it's just good to know that this is conceptually how you do it, but it might not work that well in practice. Yeah.
For x1, there's n unknowns, but isn't there just one x1?
So x1 is an n-dimensional variable, right? The state is an n-dimensional thing. So that's very important. So state is always xt is always a vector. And I had this on the previous slides, but just to reinforce it, this state is a n-dimensional vector, and the output that we observe is a p-dimensional vector, with p typically less than n. So that we don't observe something that kind of gives us the whole state every time. So, and this example I was giving here, p was equal to 1/2 of n, and so we needed 2 observations to make this kind of uniquely determined here. Now, of course, in general, you could have p much smaller than n. It could be just 1 observation, and maybe n's 100-dimensional. In that case, you would need at least 100 observations before you could determine that state. So the dimensionality of these two things really matters here. And more than just sort of the raw dimensionality, but it really matters kind of the true dimensionality of these things, right? How much information are these really giving you about n? Because if they give you redundant information, then it's not really giving you more than one measurement. So you have to make sure that it's giving you sort of a true number of independent measurements. And in fact, there has to be independence between these other things too, right? So you have to get more information from y2 than just from y1. For example, if you have this a triangulation setting, right, where you're getting a distance to a beacon and you don't move in subsequent time steps, you can stay where you are as long as you want, keep getting the same reading over and over again. It's not going to help you tell you where you are. You have to actually move around to figure out where you are. So these are all kind of these subtleties that are very interesting from these nonlinear systems that make this a very hard thing in general to know how many observations you need, for example. What this motivates, though, is thinking about a simpler case, much like we did for linear systems, motivated by the idea of controlling them and sort of talking about using dynamics as a convex constraint in optimization problems. For the same reason, there is a great motivation for you thinking about linear systems in the partially observable setting. And so what this is a special case of partially observable systems that is very, very common in practice. So this is a partially observable linear system. So it's still partially observable. We still do not know what the true state is at every time. But the dynamics and the observation are both given by linear functions here. So let me just write down sort of what all these things are. So as before in our linear system case, and remember these are all still for the time being deterministic, we have xt plus 1 being equal to A, submatrix A times xt plus B times ut. Right, where A is an n by n matrix, B is an n by m matrix. Remember the state is n-dimensional, the control is m-dimensional. And we add to this the fact that we don't really observe the state at every time. What we observe is some yt, which is also a linear function of the state. And I'll use the matrix C to denote what that is. And of course, to make these units all work out here, C has to be a matrix in R to the p times n. Now, a simple example of this would be the case of, oops, I meant to write the C transpose, and this actually should be this transpose, so ignore this for a second. I'll write the real one up here. So let's think about the scenario where we have a room where we only observe, so we have this 4-room case talked about before, which remember, the 4-room scenario here was linear, right? Because we have linear dynamics that express how temperature evolves given these 4 rooms and sort of how they are touching each other. So we have the x at time t equals the temperature of the room 1, temperature of room 2. I should just probably say, because I'm not using subscripts t, so here. So it's just the x equals temperature room 1 to 3, temperature in the 4th room, rooms 1 to 4. And suppose now that y was equal to temperature in the first 2 rooms. So we only observe temperature, what it is in the first 2 rooms of these 4. The way to express that in this system here is to say that C equals, well, the first one is just going to be the first temperatures, so that should be a 1 there and zeros elsewhere. And the second one should be the second temperature, so it should be 1, 0, and then 1 here and zeros elsewhere. So, sorry, this should actually be transposed, and I meant to write the x here. But this is the correct numbers here. Now, in general, you don't have to just observe one thermostat. I mean, maybe you put a thermostat like right between 2 rooms, for example, so that it kind of averages the temperature between these 2 rooms. And maybe you get something where your first reading was like, 1/2 of the first room's temperature, and then 1/2 of the second room's temperature. Because you have like your thermostat right on the boundary between these 2 things. That's maybe not that physically realizable there, but just conceptually you can imagine that, right? So you can observe different combinations of states. It doesn't have to be that you just observe one of, you don't observe necessarily just p of the n different actual state vectors. You can actually also observe linear combinations of them. So C can be a matrix that just gives you kind of general linear combinations of different states. But the point is that it still has to be a linear function of these states, right? The case of observing range measurements, that is not a linear function because you are not observing you're observing the distance, which is the square root of the square distance between two different points, which is not a linear function. So this model, it's important to know, you have to have C tell you that you get what you observed is some linear function of your true state. And so now the question arises, for this case, when can we, in fact, identify what x1 is given k different measurements? When can we do that? And sort of amazingly, though really there's a very good reason for this, it looks very similar to the controllability question. Can you control a system to be in some other state given k different times? That's kind of a similar question to, can you tell what the state is from some number of observations? Maybe it's not quite obvious yet, so maybe I'll just actually write out exactly what's going on here. Maybe actually, before we go to the next slide, let me just write out what the dynamics are. So for simplicity, I'll assume that all the u's, ut is going to be equal to 0. It's not hard to change that. I'm just going to write the equations a little bit. You have to just add some extra terms here. May actually do not end up affecting the system very much, so, or the answer really at all. So we'll assume ut equals 0. So we have some initial state x1. And I'm going to write out what I wrote out before, but just now for the linear case, right? So y1 here equals c times x1. That's what we observe. And now we take a step and observe another state. And so what the next state is at time t equals 2 would be just a times x1. Right? And what we observe is going to be then c times a of x1. You could add also plus bu here. That wouldn't have to change anything. So let's just, because actually, you know what? I actually will write that out. So c of x1 plus b of u1, just to sort of emphasize that this does not affect things here, which equals ca x1 plus cb u1. The point is we actually know what this thing is here because we know all the elements. So we can treat it basically as a known quantity as well. The only thing we don't know is this term here. Right? And so then, just one more time, y3 equals, well, we have to apply this one more time now. So the state's equal to axt plus bu1. So it's going to be a x1 plus bu1 plus bu2, right? Which equals, let's just distribute it out again. It'll equal a squared, or sorry, what we observe is not this. What we observe is c times this. This is y3 equals that, which equals, let's just write it out again, c a squared x1 plus c a b u1 plus c b u2. And you know, you're getting a little bit more complex here, but hopefully it's clear the only thing that will ever be unknown is this first term here, right? Because everything else, you're going to get more of these terms that involve u's and CABs and CA to the many powers and B, but these are all known. So now we have a set of linear equations where we have more than just p known variables. We have k times p variables. So for simplicity, I'll just assume that u's are all equal to 0 here, but just to emphasize the fact that this does not change anything about this, because all you would end up doing is you would just end up taking your observations and subtracting off these parts here, which you know. So we know everything but the case here. But in the simple case, what we get is, so let's just assume ut equals 0. What we get then is that y1, y2, y3 as a big vector equals, let's just write it out again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114 C, CA, CA squared. Actually, maybe I'll just let this go forever, because you can imagine that this just keeps increasing the powers there, times x1 in matrix form. And in fact, this is what I have on the next slide too. I just wanted to derive it before putting it up there. So this now is just a set of linear equations with n unknowns. And so we'll say this goes to yk. I guess this would also go to dot c a to the k minus 1. So we now have a system of k times p knowns and n unknowns. And it's just a set of linear equations. So this should look very similar to that controllability matrix I talked about before, right? Where you had a to the a squared, a to the 1, a squared, et cetera, followed by b. Here you're prefixing it with c, and you're looking at a matrix that has many different rows of this form. There you had many different columns of this form. But it's very, very similar, right? So the question is, when can we in fact determine what x1 is from all these y's? And the answer is the exact same as in the controllability case. We can do that as long as this matrix here, stacked up here, I guess this should be a to the k minus 1 for k different observations, but as long as this matrix here has n independent rows, then we can do it, right? Because then we can take those n rows, invert that matrix, and what we get is the solution to what x1 has to be. So again, the nice thing here is that for a linear system, to answer this question, can we figure out what the state is? All you have to do is form this matrix here, and then run the rank function in MATLAB. That tells you what the rank of the matrix is. If that matrix is rank n, then we know we can determine what the state is. And again, you have almost the exact same properties as with controllability here. It's hard to know beforehand whether or not this would actually be full rank. And in fact, for the case of a room that has these 4 rooms that I showed before with all equal diffusion rates, and if you have thermometers in these 2 rooms, you actually can't do it for the same reason you couldn't control that with these rooms. You basically cannot differentiate between temperatures in these bordering rooms here. Whereas if you have it in these 2 rooms, and again, you'll go through this in the homework, so you'll kind of work all this out for this and for more complex cases too. Whereas if you have it in these 2 rooms, you actually can do it. So this is observable if your measurements were these 2. And that's very hard. It's very non-obvious, right? It basically means that you form, I'm calling this like 1, 2, 3, 4 here. So if you form this as your C matrix, then it turns out you construct this thing, and it is, in fact, full rank. If this is your C matrix, and you construct it, it will not be full rank. The only way to really do this is just to form the matrices in check. You don't want to think about why this is, other than just running it and seeing what actually happens here. Yeah?
You couldn't think of it as for 1 and 4, both if you have a thermostat in both those rooms,
yep.
You're controlling.
You're not controlling anything here. You're just looking at changes. There's no actions you're taking here, because I mean, in this case, I was saying we just leave out set u to be 0. Just let the temperature diffuse as it will. We're just observing things, and the basic concept here is that If you have it in these two rooms, you're not, I mean, the only way you can figure out what temperature is in one of these other two rooms is sort of observe the effects of what temperature does to your current room, right? So essentially, if temperature is really low here, it'll make your room lower than it would be otherwise by its own internal dynamics. I mean, again, you wouldn't want to do that. What you really want to do is you want to form this matrix and just solve a linear system to actually figure out what how that is affected, really. But that's conceptually what's happening. So you can kind of guess, or you can determine what's happening in other rooms by what's happening by the effects you see in your own room. Now, the problem is if you have these two rooms, there's no way to differentiate between an effect happening here and an effect happening here. If you see temperature go down a lot, you know that one of these two has to be maybe lower than your current room, but you can't know which one it is. And that is not the case if you have them in here. But again, it's not obvious how to actually do that, to actually form this predictor. You essentially, the only way to do it is really to form the matrices here and actually construct, form this, take 4 different rows, and take the inverse of that, and that'll give you a way of finding out what it is. But other than that, I wouldn't know how to go about, doing it. Okay, so that's all we're going to say there for partially observable systems. Again, we're kind of going pretty quickly through all these things. The idea is not to give an in-depth treatment of dynamical systems or even linear dynamical systems. It's to give you some concept of what all these things are. Now, one type of dynamic, actually, that I had slides but took them out because I'm going to have a problem on this, actually, in the homework, is what are called autoregressive models. So autoregressive models, I think actually a lot of people are coming up with these in their projects. So it's good to at least see it, and then you'll be able to have a chance to sort of think about it in your assignment, in the homework assignment, and also in your project. So autoregressive models are actually kind of a form of partially observable systems, or you can think of them that way, right? Because autoregressive models say what we get is some output, and the output at time t is equal to some linear function of past outputs. So maybe t plus 1 equals a1 yt plus a2 yt minus 1 t minus 1 plus dot. And what you'll show in the homework put out next week is that you can write this in terms of a system where the state essentially keeps multiple past observations, and the output just tells you what the current latest observation is. And so this can all be written. I mean, everything's linear here, right? You can write this in the form of a linear dynamical system where you have x equals a, some big matrix a, x plus b, u. And you can express systems like this in the form of a linear dynamical system. Linear systems in general, actually, especially the partially observable ones, they're much more general than these systems. So for example, people are also in the homeworks I see, they're seeing things like ARMA models, which stand for autoregressive moving average models. Those are also a special case of linear dynamical systems. They're actually, believe for that one, that's actually fully general. So any linear dynamical system can be expressed as an ARMA model too, but we won't worry about that. Again, if you haven't seen this before, if you haven't come across these names, don't worry about it. Just know that a lot of these frameworks can be expressed using the language and using the notation of linear dynamical systems. And the point of this is just to kind of give you a broad overview of these different kinds of systems you have here, such that we can talk shortly about actually controlling them. So that's a little aside, and you'll look into that more shortly. Let's talk about one more type of system. And here I'm actually going to kind of break from the rest of the class and talk about continuous time systems, because these are almost always expressed in terms of continuous time systems. And this is a class of systems that go by the name of differential algebraic equations. Now, the idea here is that for a continuous time system, we've been talking about expressing that in terms of x dot equals f, x, and u. This is continuous time, remember. So we're talking about how the time derivatives are given by the state and the control. And we talked about how it's pretty easy, approximately, to convert this, something like this, to a discrete time system. Right? You just use Euler integration, take some time integration step, and you just do it. Now, there are some cases where you actually want to have more than just this. You want to be able to also include additional constraints on your state variables. Constraints, so they have to lie on some kind of subspace of the system. Right? And the way this is typically formulated is we add some additional variables, which we're going to call z. So this is actually going to be a function. The time derivative equals the function of x, z, and u. And where z here are called the, I'm using p again here because I'm not talking about observable. I probably should use a different letter rather than p, but sorry, p here means the dimensionality of z, not anything about partial observability anymore. So these are both state variables. X and z you can think of just as, it's kind of even a little bit, they are both state variables. It's just that the way the x's are determined are through this differential equation, as we had before. Whereas the way the z's are determined are by a set of linear, or sorry, general nonlinear equality constraints. So the other constraint we have is that some function g of these things equals 0. Where here, as I said, x is the state variables, same as before. I guess u, I'm not writing it here, but u is the control input, same as before. F talks about how the state dynamics variables evolve over time. They evolve according to this. Whereas G talks about how the algebraic variables have to evolve. Now, conceptually, and the reason why this is important here in some sense is that when you talk about something like a set of generators, they evolve according to some dynamics, namely like the dynamics of the actual physical generators themselves, right? They have some actual momentum to the system. They're big things spinning really fast. That talks about how these things, evolve over time. But they also have to satisfy power flow constraints, right? A bunch of generators hooked up to each other, as we know. We wrote down some equations for those. And those are called algebraic equations because they just are a set of equations that equal 0. Essentially, the power flow equations are algebraic equations. And as we'll see in a second, this is the way these are expressed, or the ways you can express these, is exactly through these differential algebraic equations. Now, the idea here is actually pretty simple, right? The idea is, look, this equation, and actually importantly here, g, the function g, I'll just maybe write it like this. The function x, f of x, rather, it gives time derivatives for f. So this has to output an n-dimensional vector. The other important part is that there are p, z is in rp here. So in order for this to make sense, and there to be the right number of knowns and unknowns, g has to also output a p-dimensional vector. It has to be all equal to 0. Okay? Now, conceptually, what we can do here is, this is a set of equations where we know what x is, right? We know the current state. Assume here we're fully observed. We know the current state. We know the current u. So we have p unknowns and then p knowns. So in some sense, g here is going to fully determine what the values of our algebraic variables are. So conceptually, what's happening is we're letting this equation here determine what the algebraic variables are. And then we're going to use this equation to talk about how the state variables evolve over time. So suppose that we actually could directly invert g in some sense, right? So this is kind of a little bit fuzzy what I mean here by this, but essentially, suppose we could find some function g, if I'm calling it g hat inverse, such that we could directly solve what y was given x and u. This is conceptually what happens, right? I mean, conceptually, this function determines what y is, because we know these two things, we just don't know that one. Sorry, not y, z. Did I write? I wrote y there too. Sorry about that. Z equals this function here. So if we could do this, then this is pretty simple, right? Because all we would do is we would just take this assignment and plug it into our function here. And now we're back to the land of just normal differential equations. They're a little bit more complex, but they're all nonlinear here anyway, so they don't really, doesn't really matter. So x dot here would just equal f of our little g hat inverse xu, u, which just equals some other function, right? Some other function of f, x, and u. So there's no real issue here. The problem, of course, is that we can't always invert functions analytically, right? I mean, this is the problem with, this is why we use Newton's method, is because sometimes we actually can't invert this directly. We need to actually use Newton's method to find a solution for what z is given the other assignments. And that's exactly conceptually what happens here. All we do to solve these things is we're going to use Newton's method to determine what z is given the other two variables. And then to integrate this, we take a small Euler step in that, given that value of z. So it really is not any more complex than a lot of differential equations. The only difference is to solve this, right, to solve this with Euler integration, just with a function like this, there's no real numerical iteration here, right? We just plug in our values of x and u, and we just take a step in the direction. So it's kind of easy in some sense. Here we have this additional step where we have to run Newton's method to even know what that Euler step is. So it is definitely trickier than just numerical integration. And in fact, by the way, if you're going to use something more complex than Euler integration, you have to do even more stuff that becomes even trickier. If you really want this to hold kind of exactly, use and do some interesting things with the actual Jacobians at the solution of Newton's method. But conceptually, it's pretty simple. We're just going to let this equation determine what z is, and then take a small step as we would before. So by the way, if this were, for example, a linear function, g here, you almost never see people talk about this even, because what you would do there is if it's linear and invertible, you would just determine analytically what z was from that, and you would just frame it as a differential equation. So the case where this is really mentioned are cases where you can't do that. So let's talk about the example now of what this actually is. And this is worth spending a little bit of time on because it's hopefully will bring together some of these things that seem a little mysterious in power flow, right? We talked about, oh, well, you can set the power of generators. And you set the power, and you know the power of loads, and you know the power of generators too, right? Well, how did you know what the power of generators was? How did they know to set their power to the right level? Right? The loads just change. I don't flip on a switch and tell my generator, hey, I just turned on more power. They somehow have to know what the generation really is. So this will hopefully make the whole situation appear a little bit more sensible. More complex too, but also more realistic. So when we talk about generators actually spinning, and we're talking about the differential equations of generators, remember each generator is essentially creating some voltage. They're spinning, right? They're spinning in this. They're spinning a magnet in or an electromagnet in a bunch of wires, and they're creating a time-dependent voltage. if voltage at time t equals, I guess you could call it a cosine or a sine, doesn't really matter, just your convention, but we'll say cosine here. A cosine with magnitude omega, or rather the cosine of omega t, and then plus theta. And theta, omega here is the frequency of the generator, how fast it's going. So that would be 60 hertz, ideally, for the US. And then theta here is that voltage angle that we have of the generator, right? That describes essentially what's the offset for that generator's actual way it's creating voltage. This was the exact same way of saying that a generator had some complex voltage, right? It had some voltage which we called V equals maybe V hat. I guess I should put a V hat here, sorry. Let V be equal to 1. Here I probably should, no, it's fine. I don't think you need that there. So V equals, the voltage at time t equals V hat times cosine of omega t plus theta. Again, moving back to our power systems notation here, theta is the voltage angle for that generator. We just sort of say, you know, this equaled the theta hat in polar form, it equaled this times that, e to the j theta. Remember, we sort of wrote this by ignoring what omega actually was here. We sort of said in steady state, it doesn't matter what omega is because they're all rotating at the same speed, so we're just going to ignore that and just talk about it in terms of the voltage angles here. But now let's put back those omegas, because we're actually going to talk about how those frequencies really change. So we have some angle, and really these angles are sometimes a little bit arbitrary because they can all be shifted no matter what. We need to have some sort of reference of all these things, but let's actually not worry about that for now. But this is sort of the offset of the voltage angle, and then this is the magnitude of it, and then going at some frequency. The dynamics of a generator are just a set of pretty simple differential equations, and there are even linear differential equations here. What it says is that the time derivative of the voltage angle is just, I mean, how does this change, right? Voltage angle, remember, gives us an offset, assuming we're rotating at some fixed frequency, 60 hertz. The way the voltage angle changes is we take our true frequency, which might not be quite 60 hertz, and we subtract it from the reference frequency, which I think I call there like omega reference. Right, so if our generator is spinning a little bit faster instantaneously, I mean, remember, this is sort of, it's going to be tried to be regulated very tightly around 60 hertz, but it can go a little bit faster. I mean, you turn off some appliance, and now all of a sudden it's generating a little bit too much power, it'll start speeding up. And so it starts going a little bit faster for an instant than 60 hertz. Our voltage angle will start moving forward, right? Because now all of a sudden every turn, we're starting to offset that voltage angle a little bit. The way the generator works, the way that frequency actually changes, is omega dot equals, and this is a sort of a common notation, so I'll just write it like this, equals 1 over 2h, where h here is what's called the moment of inertia of the generator. So if that's very big, has a large inertia, the time derivative will be smaller, so it'll change more slowly. And this is just like the momentum of the system, right? It's just saying the system has a lot of momentum, it'll have a big moment of inertia. It's a physical constant from the actual weight of the spinning rotor itself. So 1 over 2h times the mechanical power, that's the power we're putting into pushing on that crank, like from the actual valves we might open to push steam or gas into the turbine, minus the electrical power. So remember, what I said at the beginning way back is that essentially the mechanical power had to equal the electrical power, right? Those numbers are the same. So whatever power you put in, that's how much power the system will actually generate. Well, that's true kind of in a steady state sense. But what will really happen in practice is because there is some inertia to the system, if you just stop putting in any sort of mechanical power, it wouldn't stop immediately, right? What happened instead was it would continue spinning from some inertia, but then that would eventually stop, and it would be slowing down. You know, once this went 0, this would be negative, and so your momentum would start slowing down. Similarly, if this is more, if you have more mechanical power, maybe you lose electrical power, or some load disappears, you'll start speeding up a little bit. So hopefully this makes a little bit more sense in terms of this is really what's happening at the dynamics level of these systems, right? It's not as if you sort of know instantaneously what the mechanical power is and what the electrical power is. It's that you want to maintain some speed to the system. And if you are generating too much mechanical power, you'll start speeding up. Too little, you'll start slowing down. But you won't, the worries there are a little bit mitigated by the fact that, well, you have some inertia to your rotor. If rotors had no inertia, this would be a very bad thing, right? Because essentially they would stop instantaneously whenever power was a little bit out of balance, and that would not work, right? I mean, you couldn't do that. And so we're sort of saved a little bit by the physics of these big spinning systems. So does this make sense, sort of what's happening here physically? Yeah?
So you're saying that it's not that the generators know when they're switching off appliances, it's they're seeing that the frequency are slowing down or speeding up. Exactly.
So generators, and they'll have each will have their own way of doing that, right? And it's also sort of hopefully clarifies what's really going on when we talk about power flow. We have this weird slack generator, right, which kind of just did whatever it had to pick up the pieces. That can't really happen. I mean, there's not one generator that says, okay, you're the slack in the system, and you do whatever you want. What really happens is they all have some control running internally, and we'll talk about. I'm not going to talk about the control here because sort of I'm pushing off control until the next set of lectures, where this is just about the systems themselves. But what you can imagine is what the control really does is it will regulate this mechanical power as a function of essentially is the thing going the right speed or not. So you basically have, you might say assign. This is a simple control law, which I'll talk about this more later, but just don't worry too much yet. So you might assign the mechanical power. I have to make sure my sign is I'm getting the right sign on this here, but I might just put a negative here. You could assign the mechanical power to be omega minus omega reference. So let's see, if you are going fast, maybe then plus some maybe constant amount afterwards, plus some c that you're kind of going to guess. So if you are going too fast, now this should be negative here, right? Because if you are going faster, you want to put in less power. And if you're going too slow, you want to put in more power. So we'll talk about this next time, again, sort of control laws like this. But essentially, exactly, there's no generator here. I mean, sorry, there's no slack generator here. All there is a bunch of different generators trying to keep frequency. And they have control laws like this that sort of look at, well, what's my current frequency? Where do I want to be at? And I better adjust pretty quickly to that. Yeah?
Is that the changing?
Okay, right. So really what it is this is actually even more complex. So you typically don't say this exactly. I mean, maybe you have some constant here that is sort of your best guess for what the output should be. And then you could use a law like this, right? But you have to be changing this. So really what you do is you build actually what's called integral control, which essentially will keep the mechanical power fixed to some amount, but change it depending on what this difference is, right? So it would sort of say that actually what's really happening is that this dot equals that. That's sort of an integral type control on this thing. But we'll get to all this later. My only point here is that what's really happening in some sense is that we are picking mechanical powers generators are all on their own picking their mechanical power to try to maintain this exact amount. That's not quite true. So, I mean, what really happens is that generators, as I said before, are kind of scheduled both a day ahead and then maybe 5 minutes ahead too. So there is some level to which they do want to kind of regulate their own frequency. You actually want to do that for lots of reasons. If you start slowing down, you'll start getting off out of sync with the grid, and that can really damage your mechanical structures there if you get out of phase with the grid. So you do want to do whatever you want to maintain frequency, but really sort of some generators' entire goal is to actually try to keep the whole grid at the right frequency. So they step things up. They maybe have different control laws that are more aggressive, that step things up more aggressively to account for deviations in frequency and that kind of stuff. So it's all quite complex, but that's the basic idea of what's happening here is that generators are just spinning. They have some inertia, and they have to adjust their mechanical power they put in to equal whatever the power is. Now, as of yet, I haven't really said what this thing is here. I'm just saying there's some electrical power, right? I didn't really say what that was. But of course, we know what that has to be, right? Those things have to obey power flow constraints. So in fact, I'll even go more than this. I'll actually say I'm going to say that these are theta i's there, or sorry, theta I and omega I, and then P electrical I. So if we have n generators, these are going to be the voltage angle and frequency of the n different generators. I guess I'm using n now to talk about number of big N, talk about number of buses, because N now means the size of the states, I guess. So, here, if these are our state variables and we have N buses, we would have 2N, state variables where we have these two things for each generator. But hopefully this is all somewhat clear. Flip this. Okay. So we also know is that we don't just have this, we also have power flow equations. And the cool thing about power flows, right, is they actually are relating this power back to the voltage angle of these things, right? The magnitude too, that we can control directly. But there's also, our state variables here were these thetas, and those are also present in the power flow equations. This really sort of wraps up everything together. We can't talk about P electric here without mentioning that this depends, of course, on the actual state of the system. So in addition to these two things, we also have these power flow equations, which are algebraic equations. And so hopefully that this idea of differential algebraic systems is becoming clear now, because we have some differential equations plus a bunch of algebraic equations, which has to hold at every time. So I'm just going to write those. I'll maybe erase this, but I'll write these down here, right? So we know that Pi electric equals, at every time has to equal this, V hat I times the sum of K equals 1 to big N, V hat K, G I K times sine, it's a cosine there, yeah, sorry. Cosine theta I minus theta K plus, sorry, this thing, plus B I K sine of this difference. So this is this equation we have here. We also have reactive power, has to also be equal. So we have QI. I'll write QI electric just to make sure that I'm talking about the electric reactive power. K equals 1 to big N, V hat K, G I K sine theta I minus theta K minus B I K cosine theta I minus theta K. Okay, so that's a lot of writing there. I probably didn't need to write the power flow equations again. I mean, this is just V star. P equals V times Y, diag V times Y conjugate V conjugate. But write it out like this for now, just to emphasize that these are all algebraic equations here. So what we have now is we have this differential algebraic set of equations. And it's important to know what the state variables here are and what the algebraic variables here are. So our state variables in this case, these are the ones, remember, that evolve according to our dynamics. So our state variable x equals the voltage angles and the frequencies, but only for our generators. Remember, we also have generators. We don't have two types of generators now. We don't have like a slack generator and a PV generator. They're just generators. That's what they really are in practice. Again, with some qualifications of some have sort of different goals, subtly speaking. But our state variables, these are the ones that evolve according to these differential equations here, are just all the generators. Remember, there are n total nodes, but some of those nodes could be loads, and some could be generators. So these are our state variables. Our algebraic variables now are the things that we don't, things that are given by these equations here, but which we don't control directly. And so it's written down there, but hopefully it makes sense what these things are, right? For the generators, the things we don't know is, well, we don't know the electric power. Sort of different from power flow, where you think you do know the power, really. But we don't know the power here. We just know how these equations, which will prescribe what the power is, depending on power flow, according to power flow laws. And we, of course, also don't know what the reactive power is. This is for our generators. For the loads, the PQ loads, we do know what these things are. But there are other variables here. I mean, the theta, the voltage angles for the loads still matter, of course, right? I mean, those are important to know what those things are, and as well as the voltage magnitudes for the loads. So for the loads, the algebraic variables are the voltage magnitude and the voltage angle. This is for the I's that are loads. And finally, the things we can control, the knobs we can turn, are, well, we can control the power, the mechanical power. We can't control directly the electrical power. That's determined by power flow, but we can determine what the mechanical power is. And though this is a little bit more subtle here, we can also actually control the voltage magnitude of the generators. The way you do this is you put more current through your electromagnet. We talked about in the very first lecture on power systems, I think. You run more current through a loop of wire around a magnet, and it'll create more voltage system. Create a higher, a stronger magnetic field, which will create more voltage. And these are for only the generators. So let's make sure everything sort of adds up here. There are, let's say that there are n sub g generators and n buses. So, and big N minus ng loads and ng generators. In that case, well, x, and I'll just erase these, hopefully that'll be obvious. I guess the size of the state, right, will be 2 times ng. So we have 2 state variables for each generator, the voltage angle and the frequency. This guy here, well, we have 2 variables for every single bus. So they're going to be 2n algebraic variables. And then we're going to have also 2 ng control variables. Just to make sure this all makes sense, remember the dimensionality of our differential equations had to be the same as the number of differential state variables. And here, of course, we have one of these for every generator, so we have 2 ng of these. So that checks out. Right, we have 2n states, 2 ng states, 2 ng differential equations. And as you would expect, we have 2n algebraic variables, and then we have real and reactive power balance for each bus in the network. So we have 2n algebraic equations. So we can this all makes sense, basically. We have the right number of equations here. And this is really what's really happening under the hood of all these power systems, right? When we talk about power flow, yes, it's sort of good to know kind of power flow is sort of a static type of analysis. But what's really happening underneath the hood is that these generators are all spinning at a certain frequency. They're all trying to keep maybe the same frequency. But it isn't exactly constant. If a new load comes on, the generators start slowing down to a very small degree, and they want to counteract that very quickly by speeding back up. So this goes by the name of keeping everything at a given frequency. It's a very important task for the grid as a whole. You do not want to stop doing that. And this goes by the name of frequency regulation, right? You have to have generators, and usually you have to have sort of special generators that just make sure they can really step up power really, really quickly, right? So because if you're operating a generator and you can't add any more mechanical power, you have to just sort of say, okay, well, I'm doing the best I can, but I'm just going to start slowing down. So they have generators that they are tasked with. They're sort of like slack generators, but there's more sort of, it's actually what's happening mechanically is these are actually able to inject more power very quickly into the system to regulate frequency, to make sure the frequency never falls too much below. There is also voltage regulation, which you do to essentially make sure that the voltage at different loads doesn't ever get too low. You can do that actually both by generator control, by stepping up voltage here, or by essentially controlling things like reactive power with things like capacitors. Sort of the domain of reactive power and voltage magnitude is a little bit, you have to do a little different things to do those things. But essentially, the mechanical power is what's used to regulate frequency. And oftentimes people will use voltage or other things to regulate both reactive power and the actual voltage magnitudes or voltage angles themselves. That last little bit, that can be all sort of parenthetical. It's not the important part here. But if you have heard the terms of frequency regulation or voltage regulation, that's what's happening here. So I believe we're about out of time here. Yes, so this gets pretty, as you can see, these things get pretty complex pretty quickly, right? But this really is the dynamics of how power evolves on the grid. You have both a set of dynamical equations, dynamical systems, governing the generators, and a set of power flow equations governing the laws of electricity. Because these operate really, I guess electricity travels at the speed of light, so these effectively happen instantaneously, whereas these happen on time because we can actually measure and see. So it's really interesting, sort of the interplay between these things, where our algebraic variable, our state variables here, of course, still have a role in the algebraic equations because it's what matters. But these things are all tied together really, really nicely. So next time we'll talk about stochastic systems, and that is what happens when there's noise in the system, or we don't know what's going to happen in the future. And then we'll start talking about actual control. How do you write the laws to really control these things? Again, office hours tomorrow. I'll send out an email within an hour or so, reminding everyone of those times. Extra office hours on Monday then also. Homework assignments due next Tuesday, but we will not have class the following Tuesday, the week of Thanksgiving. So the other professors are nice too. Maybe you can have that week a little more free. All right, I'll see you soon.
Right.